Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 1.8 from your textbook, which introduced us to the idea of a sort of general technique for solving first-order differential equations called change of variables, or more simply, substitution. In the previous video, we took a look at a very specific type of first-order differential equation, which we called homogeneous of degree 0. We saw that homogeneous of degree 0 differential equations are basically differential equations that can be phrased entirely in terms of y over x. Then we used a substitution, specifically v equals y over x, to change those homogeneous of degree 0 differential equations into separable differential equations. In this video, we're going to continue with the same technique, but focus on a different type of differential equation and a different substitution. So, for this, just like before, we're going to start with a definition, then prove a quick theorem to show that this substitution will always change this format of differential equation into something that we've already seen, namely a linear differential equation, and then we'll take a look at a couple examples. So, for our definition here, a first-order differential equation is said to be a Bernoulli differential equation if it can be written in the following format: y prime plus p of xy equals q of xy to the n. Now, this format should look pretty similar. You'll notice that if this term wasn't here, if that y to the n wasn't there, then this would be the standard form for a linear differential equation. The only difference here is that this is non-linear because of that y to the n term. So the idea here is that because this is very close to linear, we're going to see how a transformation, basically a change variable, can make this into a linear differential equation. But in terms of identifying Bernoulli differential equations, you should basically be looking at something linear where the only nonlinear factor is a y to a particular power. All right, so how are we going to sort of deal with these? Well, what we're going to do is if we have a first-order differential equation that is Bernoulli, then the substitution or change of variables, u equals y to the 1 minus n. So we use u equals y to the 1 minus n, where n is that power here in this sort of original definition, so that n is carrying down there. Then that is going to convert it into a linear differential equation in terms of u and x. So the guarantee here is that if you have something that starts off Bernoulli and you apply this change of variable, then you will result in something that is guaranteed to be linear. So let's go ahead and prove that. So what we're going to do is, just like we did in the sort of previous video, we'll go through, take a look at this substitution, plug in this substitution, and then see if we can rewrite the Bernoulli differential equation into a linear format. So let's go ahead and take a look at that. So we've got y prime plus p of xy equals q of x y to the n. Right? We know we can start with that because we're assuming that we have a Bernoulli differential equation to begin with. And we're told that we should try to use this substitution. So let's have u be equal to y to the 1 minus n, and let's take the derivative with respect to x here. Now, of course, x, we don't actually see that, but both of these are being treated as dependent variables here. So if we do that, we would get 1 minus n, y, and then, of course, we would subtract 1 from this exponent, so we get to the negative n, and then we'd get the derivative of y with respect to x. And, of course, that right there would be chain rule. So we're saying that u prime would be equal to this expression. Now, it might not be immediately clear where we're going to sort of find this expression here. So let's hold off for a second. We'll just keep this substitution there, and we'll try to manipulate this form a little bit. Notice that our substitution involves y to the 1 minus n and y to the negative n. So it might be a good idea to divide through by y to the n. So let's take our original Bernoulli differential equation and divide through by y to the n. If we do that, we'd get y to the negative n, y prime, plus p of x, and since this is a y to the 1, dividing by the y to the n is going to give us y to the 1 minus n. And just to make sure we're clear, my prime is a little, we should slant it a little bit more, make sure we're clear that's not a y to the 1, equals q of x. Okay, now notice this is looking better because this u equals y to the 1 minus n, that can be subbed in here, and this is beginning to resemble this. The only thing that's off is that we're supposed to have a 1 minus n constant, but we can, of course, divide that over, and if we just think about our substitution a little bit more, we can think about it as 1 over 1 minus n, u prime, equals y to the negative n, y prime. Now we can replace this into here. And if we do that, we should get 1 over 1 minus n u prime. That entire expression is going to take care of what we had here, plus p of x. This y to the 1 minus n is exactly equivalent to u, so we have u equals q of x. Now, actually, this we could just call it good here. We could put our check mark or our QED or whatever we like, because this is certainly linear in terms of the variable u, because notice that our u is being the dependent variable. There is no function of u or any of its derivatives, and they are in separate terms. If we want to make that a little bit clearer and we want to put it in standard form, all we would have to do is multiply by 1 minus n, and we'd get u prime plus 1 minus n times p of x. U is equal to 1 minus n times q of x. And there we go. Now that actually is linear and in standard form. So it's very clear that this substitution has made our differential equation into something that is linear. So there we go. We've proven this here. So this proof, not just like in the previous one, not only tells us what the substitution is going to do, but it also just sort of tells us computationally what the general idea is. We know that we're going to be using this substitution, and we also know that when we do that substitution, we're not expecting it to be a perfect substitution initially. We're probably going to have to play around with it a little bit, especially with that constant, before we're able to just plug in directly. Notice it also tells us that this format with the y to the n is how we identify a Bernoulli, but we actually do the substitution by dividing the y over n onto the other side, and it's from this format that we actually apply the substitution. So Bernoullis are a little bit tricky here just because we use this format to identify that something is Bernoulli, and we use this format to actually plug in the substitution. However, we now have this theorem that tells us that if something is Bernoulli and we apply this substitution, we know it will always result in a linear differential equation. Also should probably go without saying, but just like in the homogeneous of degree 0, just like with any substitution, this substitution does not solve the differential equation for you. It simply puts it into a different form that hopefully we know how to solve. And that is absolutely the case because we are very comfortable solving linear first-order differential equations. Okay, let's go ahead and get into some examples here. All right, so for our first example, we're going to try to find all solutions to this differential equation. Now, as we know, because we're in the second video of 1.8, we know it's going to be a Bernoulli example because that's the technique we just learned. But let's think about why this shouldn't be anything else, why the other techniques we have aren't going to really apply. So, first of all, you can throw out linear right away. Why? Because we have a y squared. And it's even worse, it's a y squared in the denominator. So that's basically a y to the negative 2. That's a function of the dependent variable. This thing is definitely not linear in its current form. Is it separable? Well, we're not particularly thrilled to see two separate terms. If I bring this over to the other side, there's two terms that both involve x's and y's. It would be very hard to factor that. In fact, impossible to factor that, so it's not going to be separable. Maybe it's homogeneous of degree 0. Well, we're not particularly thrilled by that either because we don't see any y over x's as compositions. We don't see like an e to the y over x or anything. And we don't have exclusively polynomial terms of the same degree. So none of the sort of previous techniques we've discussed so far really apply here. So hopefully it is Bernoulli. Can we see this as Bernoulli? Well, yeah, if we remember, the thing we said that made it nonlinear is that y squared in the denominator. So we can rewrite that as y to an exponent, and that basically puts it into a Bernoulli format. So we say y prime minus 2 over 3xy is actually going to be x squared e to the x over 3 times y to the minus 2. And that right there now tells us that this thing is Bernoulli. This is in the correct Bernoulli format. There's the sort of p of x, there's the q of x, and there's our y to our n. So we know our substitution is supposed to be u equals y to the 1 minus, and since we've got a negative 2 there, we'd say 1 minus negative 2, which means our substitution is going to be u equals y cubed. We also should write out our derivative. We're going to get u prime is 3y squared y prime. Okay, now we know that to start actually finding these things in here, we don't see any of this stuff in this current format. So let's go ahead and multiply this over onto the other side. So we're going to multiply by y squared, or I guess divide by y to the negative 2. Since it's really a multiplication by y squared, we don't have to worry about getting any extra solutions. So we just multiply that over, y squared y prime minus 2 over 3x y cubed is equal to x squared e to the x over 3. Okay, at this point, we can sort of start to see, okay, this looks good. That's going to be our u there. This is looking closer to what we want. We can just do a slight modification and divide the 3 over, and we can see that 1/3 u prime is going to be y squared y prime. Now we can use that to plug into here. All right, so let's go ahead and do that. We get 1/3 u prime minus 2 over 3x. This y cubed is now equal to u, so we have our u there, and we have x squared e to the x over 3. Now, at this point, this is guaranteed to be linear. We can actually see that. I mean, we know that that's true because we proved the theorem that said that that's going to happen every time, but we can see that that's true because we've got our u prime and our u, no functions of the dependent variable, and, right, they're in separate terms. It is not in standard form, though, because of that 1/3. So let's go ahead and multiply everything by 3. So u prime minus 2 over x u is going to be x squared e to the x. Okay, now this is linear and in standard form. So we can go ahead and use our integrating factor approach. It'll be e to the integral negative 2 over x dx, which should be e to the negative 2 ln x there. And if we remember our sort of standard modification from 1.6, pop that negative 2 back in here as ln x to the negative 2, then cancel those. So that's going to be x to the negative 2. So x to the negative 2 is our integrating factor. Let's multiply by that. So we get x to the minus 2 u prime minus 2x to the negative 3, because of course we can think about that as 2x to the negative 1. And then, of course, we still have our u there. And then when we multiply by x to the minus 2 on this guy, that x squared is going to cancel, and we're just going to have an e to the x. Then, since we've done linears many times, right, we know that this left-hand side here has got to be a product rule. So we can view this as x to the minus 2u prime equals e to the x. And remember, this prime here is a derivative with respect to x. Derivative of that gives us this piece. Derivative of the u gives us that piece. Now we can integrate with respect to x. So x to the negative 2u is going to be the integral of e to the x dx, which means we get x to the negative 2u is e to the x plus c. All right, we'll take this over here to finish that up. Can we do some manipulations? Well, easy to bring that x to the minus 2 by multiplying x squared on both sides. So we get u is x squared e to the x plus cx squared. Okay, now we got to undo our change of variable. We had u was actually y cubed. So we have y cubed is equal to x squared e to the x plus cx squared. Obviously, we could just leave it in this format, but since y cubed does have a full inverse, it's not a restricted inverse because the cube root is always applicable. We can get a nice explicit form by just cube rooting both sides and getting x squared e to the x plus cx squared all to the 1/3. And there we go. There's our general solution in this case. This is a general solution here because there were no other possibilities for other solutions along the way, because there was no moment where we divided by a function of the dependent variable. Here, we multiplied by y squared, so that was fine. And then once we actually had it in terms of u, we didn't do any manipulations with the dependent variable, so we know that this is our general solution there. So there we go. There's your guys' first example of working through a Bernoulli differential equation. Key idea here is being able to put it into that sort of the Bernoulli standard format, which is that y prime minus a function of the independent variable times y equals a function of the independent variable times y to an exponent. Trick here was to recognize the y squared in the denominator as a y to the minus 2. Choose the right change of variable right here that we did in u. Make sure that we manipulate the u prime a little bit. It wasn't a perfect substitution. We got that extra factor of 1/3. Pop that in there. Then we knew it was linear. Had to put it in standard form. And once it's linear in standard form, it should be nice and easy all through here. Okay, let's go ahead and take a look at another example. So, same idea. We're going to try to find all the solutions to this differential equaton. Apparently missed the I in there. So it is a differential equation, not an equaton, though that sounds like something that would be weirdly discovered in chemistry or something about the atom. Anyway, I digress. So let's go ahead and take a look at this. How do we know that this isn't anything else? Well, again, not going to be very separable because we've got two terms here, and there's no way to factor, so both the terms involve both x and y. So that's not going to be separable. Certainly not linear because you have a function of y, square root of y there. But it is a function where the function that's being applied to y is just an exponent. So that sort of hints at Bernoulli. And of course, there's no functions of y over x in here. So we're not hopeful that it's homogeneous at degree 0. So most likely this is a Bernoulli. Let's go ahead and try to rewrite it into that format. So let's bring that minus 8y over, and we can view this as xy prime plus 8y equals 2x ln x. And let's get rid of that square root of y and just view it as y to the 1/2. That'll help a little bit because that's what it's supposed to look like. We could proceed right from here, except it's not quite in the Bernoulli standard form. There's not supposed to be any x or anything attached to the y prime. So let's divide by that first. And we get y prime plus 8 over xy is 2 ln x y to the 1/2. Again, don't have to worry about that division because that's just assuming x is not equal to 0, which is a domain restriction. It's not a restriction on the actual functional solutions. So there we go. Now this is Bernoulli here. This is exactly the Bernoulli format. So we are going to do our substitution. U equals y to the 1 minus, and our exponent here is 1/2. So 1 minus 1/2, which means we're actually doing our substitution of u equals y to the 1/2. That means u prime is going to be 1/2 y to the negative 1/2 y prime. And again, we probably are going to have to manipulate that in a moment, but let's go ahead and first actually just identify these things here. Remember, that means that we should take this and divide it through. So let's go ahead and divide that. Y to the negative 1/2 y prime plus 8 over x. If you divide y by y to the 1/2, you'll get y to the 1/2 equals 2 ln x. Now, of course, when we did that division by y to the 1/2, that was a division, so we have to assume that y to the 1/2 is not equal to 0. We'll think about that a little bit later on. Okay, now we're here, looking pretty good. The y to the 1/2, that's our u. The y to the negative 1/2 y prime is almost what we have here, so let's just do a quick modification. Let's bring the 2 over there. And we can say 2u prime is equal to y to the minus 1/2 y prime. Could we also just make the 1/2 y to the negative 1/2 y prime appear? Sure, if you wanted to, you could divide everything in your equation by 2 and put a 1/2 there so that you could just directly do that. Now, that's a fancier way. That's actually probably a better way of doing it, but the way I'm sort of showing each time where we actually manipulate the 2 over to get exactly this, that's just more of sort of a brute force, guaranteed to work every time, doesn't really take any extra thought. But if you can sort of just recognize that if you divide everything by 2 right now, you can build this expression, then feel free to do that as well. For now, though, we'll go ahead and replace this y to the negative 1/2 y prime is equivalent to that 2u prime. So this is 2u prime. Plus this y to the 1/2 is u. So we have 8 over x u. And then on the right-hand side, we have that 2 ln x. Okay, at this point, this is now linear. But it is not in standard form because of that 2, so we do need to divide by 2. Notice you could have divided by 2 earlier. Now you can divide by 2 here. Doesn't matter. Divide by 2, we get u prime is plus 4 over x u is equal to ln x. Now this is linear and in standard form. So we can go ahead and come up with our integrating factor, which is e to the integral 4 over x dx, which is e to the 4 ln x. Again, trick, put the 4 in there, x to the 4th, cancel out the ln. There's our integrating factor, x to the 4th. Let's multiply everything by that. We get x to the 4th u prime plus 4x cubed u equals x to the 4th ln x. Now, we can recognize the left-hand side as a product rule. It's x to the 4th u prime, again, derivative with respect to x, equals x to the 4th ln x. Now we can integrate both sides with respect to x. That'll remove the derivative on the left-hand side. So x to the 4th u is equal to the integral x to the 4th ln x dx. we're done on the left-hand side, but we will need to figure out this integral. This is a product, so it's probably going to be an integration by parts. So let's go ahead and grab this real quick. We'll do it on a separate page and then come back and finish this up. So let's zoom in a little bit. We've got the integral x to the fourth ln x dx. This is an integration by parts. This is an integration by parts where actually you do not want to differentiate the polynomial. Usually you differentiate the polynomial term to reduce the exponent, but we don't want to actually have to integrate that ln, and if we differentiate the ln, it becomes much simpler. So we'll actually let the u be equal to ln x, and the dv be x to the fourth dx. The du then will be 1 over x dx, and the v will be 1/5 x to the fifth. We pop that stuff in. Our vu is going to be 1/5 x to the fifth ln x minus the integral of that v du, which looks like it's going to be 1/5 x to the fourth dx. Then we can go ahead and finish up this integral with another power rule. 1/5 x to the fifth ln x minus 1/25 x to the fifth. And of course, we'll get a plus c there. Of course, we just remember to put that on our next page. So let's grab that, pop that back over there. So if we do that, we can take this over to here, and we get x to the fourth u is now equal to 1/5 x to the fifth ln x minus 1/5, or 1/25th, I believe. 1/25th. Yep, 1/25th x to the fifth plus c. So there we go. There's our solution on the right-hand side. Now we can sort of clean this thing up by dividing by that x to the fourth. That's not too bad. So we get u is 1/5 x ln x minus 1/25th x plus, I guess we could just call it cx to the negative 4. All right, now we have our replacement of u, which was y to the 1/2. So I guess we could say y to the 1/2 is supposed to be 1/5 x ln x minus 1 over 25 x plus cx to the minus 4. Could we square both sides? Sure. The only thing I'm concerned about with that is, again, squaring and square rooting are only inverses on like the positive half. Here it should be sort of safe there. But again, I would just be a little bit cautious with that. I think this is a totally fine format to sort of leave that in. We do need to consider that one sort of additional possible solution here. So let's go back and just consider this real quick. We'll just pop that over to the side here. This, of course, would mean that we'd have to check like y equals 0. So when is y to the 1/2 potentially 0? It would be when y is 0. So if we check y equals 0 back in this original differential equation, well, if y is equal to 0, left-hand side is certainly equal to 0. Right-hand side is also going to be equal to 0. So that does work as a solution. So we would need to include that on our list here. Certainly there's no choice of a constant where this is going to just be equivalent to y equals 0 because it's always going to have this stuff too. So our solution set, if we say that, should be things of this form along with y equals 0. So there we go. There's our solution set on this one. Probably you can't really say that this one has a general solution because that y equals 0 there is not part of that family. All right, so at this point, we've done 2 examples of going through and looking at Bernoulli differential equations, trying to get more comfortable with this change of variable substitution. Let's wrap this up with, as we sort of always do, with at least one example of using this technique on an IVP, and again, just getting a little bit more practice with this. So let's turn to our last example here. For this last example, we're going to consider this differential equation. We're going to prove that every IVP for this differential equation will have a unique solution. So we're going to prove that for every IVP, this guy will have a unique solution. Then we're going to find the unique solution to 2 different IVPs, one with y of 0 equal to 1 and one with y of 0 equals 0. So let's start with part A, trying to prove that this thing has a unique solution for every IVP. So to do that, we'd like to use that existence and uniqueness theorem for first order differential equations. Why do we want to use the one for first order? Well, of course, I mean, it is first order, and there is no hope for this thing being linear since we have that y cubed. So we've got to use the existence and uniqueness theorem that applies in general as long as things are first order. If we do that, we can sort of rephrase the differential equation as y prime is 1/2 y minus x to the fourth y cubed over 2e to the x. We can then see that this has f of xy in terms of the phrasing of the existence and uniqueness theorem as 1/2 y minus x to the fourth y cubed over 2e to the x. Are there some issues with continuity? There could be with that 2e to the x in the denominator, but as we know, e to the x is never 0. So this is definitely continuous everywhere. So this is continuous everywhere. And if we look at the partial with respect to y, well, we would get 1/2 minus this, all this stuff. And you might think quotient rule, but again, only the y cubed is being treated as a variable. So it's actually a little bit easier. It's just 3x to the fourth y squared over 2e to the x. And since that has the exact same denominator, and again, e to the x is never equal to 0, that is continuous everywhere. So that tells us, by the existence and uniqueness theorem for first order diffeq, every IVP will have unique solution. So every IVP out there will have a unique solution because the function and the partial with respect to y, in terms of this presentation, y prime equals a function of both x and y, are guaranteed to be continuous everywhere. So every IVP will have a rectangle of continuity around it. That means every IVP is going to have a unique solution. So now that we've established that, we can go ahead and find the unique solution in each of these situations. So let's go ahead and do that. So for B, we're going to, now that we have that information, attempt to solve this with y of 0 equal to 1. So we know we're operating around where x is equal to 0 and y is equal to 1. That's the initial condition that it must pass through. So let's go ahead then and take a look at how we would actually solve this. Like we said, it's definitely nonlinear because of the y cubed. That hints at it being Bernoulli. So we'd like the y cubed term over here, and we'd like the y term over here. So let's rearrange this. This is y prime minus 1/2 y is equal to minus, and just to make it a little bit easier to visualize, I'm going to write it as x to the fourth over 2e to the x, sort of as a coefficient function, and then the y cubed there. So this thing here is Bernoulli. In terms of it being Bernoulli, what substitution should we do? Well, it's going to be u equals y to the 1 minus, and our exponent here is 3. So 1 minus 3, which is going to be y to the minus 2. And that means u prime is going to be minus 2y to the minus 3 y prime. All right, so at this point, we need to sort of manipulate this a little bit further. Let's go ahead and divide the y over to sort of build these expressions. So we get y to the minus 3 y prime minus 1/2 y to the minus 2 is minus x to the fourth over 2e to the x. Should we be concerned about like the potential that y equals 0? Well, y equals 0, that is definitely a solution to this, but is y equals 0 going to satisfy that IVP? Well, no, right? If y equals 0, then certainly y at 0 is not going to be 1. Y is always going to be 0. So we don't need to worry about y equals 0 because that does not satisfy the initial condition. That's not a solution to this IVP. So we can go ahead and proceed forward without having to worry about that y equals 0 potential. Okay, at this point, we almost have this. Now, again, you guys have sort of options. You could multiply this entire equation by -2 to make sure you build that expression, or you could go ahead and do it like we've been doing, which is to divide this over. Just to stay consistent, that's how I'll write it out. Minus 1/2 u prime is going to be y to the minus 3 y prime. But again, nothing wrong with if you multiplied everything here by -2. Let's go ahead and pop that in then. So that's going to be minus 1/2 u prime minus 1/2 u is equal to minus x to the fourth over 2e to the x. So that's just plugging in this substitution in for this. And of course, our u is y to the minus 2. So we just plug it in right there. All right, now this is indeed linear. We can put it into standard form by multiplying by -2. So again, your choice when you want to do that. If you multiply by -2, looks like we should get u prime plus u equals x to the fourth over e to the x. So there we go. Now this is linear and in standard form. So let's go ahead and grab that integrating factor. The integrating factor here is going to be the integral e to the integral of 1, because there's just an implicit 1 in front of there, dx, which means we get e to the x. So if we multiply both sides by our integrating factor, we would get e to the x u prime plus e to the x u. And if we multiply this side on e to the x, it's going to cancel that out. So we get x to the 4th. All right, we'll finish this up on the same page. So I'll just give myself a little line there so we can separate that. Pull that over to there. We can recognize that left-hand side as a product rule. That's e to the x u and then prime equals x to the 4th. Perfect. Now we can integrate both sides with respect to x. E to the x u is the integral x to the 4th dx. That means e to the x u is 1/5 x to the 5th plus c. So there we go. If we want, we can go ahead and, I guess, divide by that e to the x to get an explicit form for the u. So 1/5 x to the 5th e to the negative x plus c e to the negative x, I guess we could call it, or we could write this whole thing over e to the x, whatever you sort of like. And then we can plug back in that y, or u was y to the negative 2. So we get y to the negative 2 is equal to 1/5 x to the 5th e to the minus x plus c e to the negative x. Okay, so there we go. We could try to get an explicit form, but it's going to be pretty hard to do that because at some point we're going to have to square root. We could certainly put all this as a reciprocal to get rid of the negative exponent, but I would avoid square rooting again because it's only a limited inverse. So let's go ahead and find the value of c. Our initial condition is y of 0 is equal to 1. So we have y of 0 equals 1. If we plug that in over here, we're going to get 1 to the minus 2, which of course is just still 1. So we get 1 equals. If we plug in 0 here, that term's going to drop out, and this is just going to become a c. So we get 1 equals c. So our unique solution is y to the minus 2 equals 1/5 x to the 5th e to the negative x plus e to the negative x. So there's our unique solution to that IVP. Could we rewrite it a little bit? Like I said, definitely, if you want, you could do the reciprocal of both sides and make it something like y squared is 1 over 1/5 x to the 5th e to the minus x plus e to the minus x if you want. I don't know if that's much better, though. Certainly want to avoid square rooting it, though, because, again, that's a limited inverse. So there we go. There's our unique solution. Now, if we think about it, we had one more part that we wanted to do. We want to try to find the unique solution for the IVP with y of 0 equals 0. So we might say, well, this should be pretty easy. We could just go back to right here and try y of 0 equals 0. If you think about that, though, if you try to do y of 0 equals 0, you plug in 0 on this side. That's easy. It'll get c. But if you try to plug it in on the left-hand side, you get 0 to the minus 2, which is undefined. So this somehow doesn't work for our other IVP. But we know every IVP has a unique solution. So is something wrong for part C? I mean, if we can't solve y of 0 equals 0, if we can't find the constant, are we stuck? Did we make a mistake? Well, it's actually because if we change that initial condition and we do y of 0 equals 0 for part C, then in this moment when we divided by that y cubed, well, y equals 0 would be our unique solution. So, if we take one more sort of page to look at that, if we look at part C, and we start off with that sort of y prime minus 1/2 y equals x to the 4th over 2 e to the x y cubed, and remember that we have our y of 0 equals 0, in that moment, I'm not going to write out the whole substitution, but in the moment where you divide that y cubed over, notice that that makes the assumption that y is not equal to 0. But we want y to be equal to 0 at its initial condition. So the unique solution here would be y equals 0. And we know we don't have to worry about any other potential solutions because we know from part A, every IVP has a unique solution. So this one, we just have that unique equilibrium solution, y equals 0. If you guys are ever finding yourself when you have a sort of setup like this and you take an initial condition and you try to solve for C and you cannot, you get something that is undefined, or you simply cannot solve for C, you don't get any values of C. What that probably means is that somewhere along the line, you made an assumption that y was not equal to a specific value or a specific function, and that specific value or that specific function is actually the unique solution you wanted. So I just want you guys to sort of compare and contrast B and C here. For B, because we had the initial condition where y of 0 was equal to 1, we actually solved the full differential equation, plugged in the initial conditions, and found that unique functional solution that actually came from this family. But for this one, where y of 0 equals 0, that unique solution would be the assumption that we sort of made to even do the Bernoulli, that y was not equal to 0. It would actually be that solution there. So just so you can sort of compare and contrast part B and part C here. Notice also this is just another reminder of how important it is to know that every IVP has a unique solution, because that sort of guarantees not only that it's unique, but we're proving that it has a solution. So we knew this one had a solution, and even though we couldn't find it in here, that meant we had to go back and find it somewhere else, which must have been in that sort of division step. So this is going to wrap up section 1.8 from your guys' textbook. In the next video, we'll be moving into section 1.9, which looks at one last type of first-order differential equation that we're going to learn how to solve.